Can't speak today. But what I want to know now is what is the voltage drop? How much voltage came into this point right here? Now, because of these numbers, there's a whole bunch of different ways we can solve this. But I want to know what the voltage potential coming in here is. We're going to call this the voltage at node C. Now, we know the voltage drop would be equivalent to the resistance times the current flow. So we can simply take 47 times the 149.5 milliamps. And the voltage drop across R1, so V of R1, is going to be equal to 7.2 volts. That is the drop. That's how much we lost of the original source going across R1. So what we could say is if we do 9 minus the voltage drop, and that means the voltage going into this point right here will be equivalent to 1.98 volts. So we lost 7.2 across this resistor, and now we have 1.98 volts going into these two branches. And if that is right, if all my math is correct, if we were to take the resistance value or the voltage value divided by the resistance, we should get this same current flow. So the voltage was 1.98. We're going to divide that by 22. It came out to 90, or roughly rounded up there, so 89.7. So now we know we're correct. So we have 1.98 volts coming into node C. We had 149.5 milliamps coming into node C. They branched out. The voltage potential across both of these resistors, because they're in parallel, would be the same. So the whole voltage drop across here is going to be that. But the current flow is going to be split. So in parallel, it splits the current. In series, we have voltage drops. So in this case, we have this amount of current going through R1, this amount going through R2, this amount going through R1. The voltage drop across R1 is here, and the amount of voltage coming into here, or the voltage drop across there, will be 1.9. The last thing that we may want to find is what is the power consumption of each of these resistors. How much power is being consumed? And at that point, the power equation, or the power consumed by a specific resistor, so I'm just looking at this one for right now. So P of R2 is going to be equal to the voltage drop across that times the current flow through that resistor. So we know the voltage is being 1.98. We're going to multiply that by the current of 0.0897. So the power consumption here would be 177 milliwatts. So that is the power consumed by the resistor, dissipated by resistor 2. We did the same thing for resistor 3. Going right in R. It would be the voltage drop across resistor 3 times the current passing through resistor 3. We have the voltage drop and we have the current. So do 1.98 times 0.598, and we get 118.4 milliwatts. And then lastly, we'll look at R1. We had a voltage drop of 7.02 and a current flow of 149.5 milliamps. We would have gotten a power consumption at R1 equal to 1.04 watts.